This is exercise 3C, question 9. Let me show you in the book. Down here, this question. So we've got a function. I should have written that as f of t. Some number times t, e to the power of b t squared. It has a maximum value of 1 when t equals 2. A maximum value of 1. Right, so it has a point that equals 1 when t equals 2. It's also a maximum, so it's a stationary point. Right over here, stationary point. Stationary. Therefore, the derivative, and let me write it properly in function notation, we could say the derivative will equal 0 when t equals 2. In fact, why didn't I write that? Not sure, but I will now. That's better. So if we can find the derivative, we put 2 in, we'd get an answer of 0. It told us the nature of the stationary point. It was a maximum. Now they're using t's. That's instead of x's, right? We've got some function. T is most likely standing for time. And there. And, we've got a little point there, right? A little max. Make sense? Okay. Now, I like to do this before the derivative, but the order doesn't really matter. I like to, if they're giving me a point, and I've got unknowns, a's and b's, I will put the values in so that 2 goes where the t is. It's like the x value. And the function needs to be giving an answer of 1. So f of 2 has to equal 1, and therefore it follows that 2a e, now 2 squared is 4, so it'll be a 4b equals 1. Or I could say a e to the 4b equals a half. I could get an expression for a, but I think I might just leave that. Right, but even so, it looks a bit simpler now that the t's have been made into the number 2, and I've made the function equal to 1. So that's something we'll be using later. Let's now look at the derivative. We have a function. We have a product rule situation. We have a product. Hopefully you're seeing this. At times e to the power of t squared. So our first function is at. That derivative is a. Our second function is e to the power of bt squared. We find the derivative outside, right, with e to the power of x, or e to the power of f of x is its own derivative. That's the outside, but then we still have to multiply by the derivative of the inside, so we're really applying the chain rule here. And now let's work out what the derivative is. So we've got OOV here, a e b t squared, and then we've got OOV again. Product rule, we plus, so we've got at, oh, hang on, I've made a mistake. It's not just 2t, the b constant still needs to be there. Put it in there, that's better. So it's actually an a, let me put the number first. We've got 2tb times at, and then I'll put the e to the bt squared at the end. We've got 2 let's do it a, b, we've got a t times a t, that's a t squared. So did I get everything? I think so. 2tb, 2tb, and an a and a t, yep. And then we've got the same e to the power of expression that we had over here. So this could be factorized. Let's do that. To e1 plus, so what are we pulling out here? The a and the e. We're left with 2b t squared. Right. There's our derivative. Now, we know that we have a stationary point, a maximum, so that if I plug 2 into the derivative function, so let's do that up here. We get an answer of 0, so therefore a, e, now t is 2, so we'll have 4b there. Right, so I've plugged 2 in here. I need to plug 2 in there. That'll equal 4. This will be 4 times 2, so that makes 8. So we've got 1 plus 8b, and all of that equals 0. Because the gradient is 0 there, the function becomes stationary at that t value of t. Now this bit here can never make a 0, right? I'm talking about that, right? There's no a's or b's. Well, there is actually. I could make a equal to 0, couldn't I? But if I made a equal 0, over here in the function, that would just, the whole function would equal 0. So it's like, that would kind of ruin the entire function. I suppose you could make a statement somewhere, a is not equal to 0. But certainly whatever the b is, right, because it's in a power, there's no way to get you 0 there, but there is a way to get a 0 here. So we could say something like, therefore 1 plus 8b has to equal 0. That will make the whole function 0. 8b will equal minus 1. b equals minus 1/8. Nice and easy. Okay, if b equals minus 1/8, we can find a. Over here, we had a nice expression. Right, we could say sub b equals minus 1/8 into, let's call this equation 1. Right. So I would get a times, now what's 4 times minus 1/8? 4 times an eighth is a half, or 4 on 8, and it's a minus as well. So I've got e minus a half equals a half. I just want to know what the a is. A equals 1/2 divided by e to the minus a half. I'm going to write that differently. E to the minus a half is 1 on square root e, right? So e to the minus a half, deal with the minus, put it on the bottom of a fraction, half is square root. And I need to divide by that to leave a. So over here, divide. Now, therefore, I'm running out of room. Maybe I can fit it in here. A equals a half times square root e on 1. A equals square root e on 2. All right. So there you go, we found a and b, and that's what we needed to do in this question. I had a few people ask about this one. It's really always the same sort of procedure. When you have two unknowns, you'll need two equations. to find your unknowns. And so we can get to equations because we can use the derivative, right? And the function as well. So there's been quite a few questions in chapter 2 and 3 that are really revolving around simultaneous equations and solving them. But I guess the algebra is certainly a step up this year compared to last year. So what I wanted to show you was what this function actually looks like now. So now that I know what the a is and I know what the b is, where did I write it? There. I put them in because I was wondering, what does it look like? So I typed it into Desmos here. So the a was square root e on 2, the b was minus 1/8, and the t, which I've called x, was squared. And it kind of makes this nice little curve. It's not a bell-shaped curve. Skews off here, but yeah, you might have been interested to see what it looked like. You can maybe think about this part of the function here. If you just ignore the e bit, that would be like a straight line, wouldn't it? Sort of pushing it up at the start, where when x is a very small value here, this wouldn't have much influence, but then this will take over because it's an exponential but to the minus power, so we'll get this decay, right? So it's almost like you've got, I don't know, growth and decay in the same function. Is there a way I can do that? Yeah, so the start of the function pushes it up, and then the second half of the function sort of gets it to decay back down. Anywho, interesting. Hope you enjoyed that.